The next type of double replacement reactions we're going to learn about are acid-base neutralizations. Before we jump into writing the molecular, ionic, and net ionic equations, we first need to talk about acids and bases in general. Acids are typically substances that have a low pH value, less than 7, whereas bases are substances that have a high pH that is greater than 7. There are a few acid-base theories that are known throughout chemistry: the Lewis theory, the Bronsted-Lowry theory, and the Arrhenius theory. For this class, we're going to focus on only the Arrhenius theory. If you take Chemistry 112, the second half of this course, we will learn about the Bronsted-Lowry theory and the Lewis theory there. Let's look at a few definitions. An Arrhenius acid is a substance that produces hydronium ions, which is H3O+, in water specifically. That means if you were to take an acid such as hydrochloric acid and dissolve it in water, it would break up into two substances. It'd break up into hydronium ions and chloride anions. Hydronium ions is often shortened by writing H+. H+ is called a proton. So throughout your textbook and throughout your notes, you might notice that H3O+ and H+ are used interchangeably. They mean the same thing. A hydrogen ion, or a proton, will combine with water in solution to form a hydronium ion, or H3O+. So proton is just the shorthand notation of an aqueous hydrogen ion. An Arrhenius base, on the other hand, is a substance that produces hydroxide ions in water. So they're substances that give rise to OH-. An example would be something like sodium hydroxide. If you were to dissolve sodium hydroxide in water, it would break up into two species, a sodium ion and a hydroxide ion. So we say that it dissociates into sodium ions and hydroxide anions. And HCl would dissociate into protons and chloride anions. So the word dissociate just means it breaks up into those substances. An acid-base reaction is one where a hydrogen ion, or a proton, is transferred from one chemical species to another. So for example, when we take HCl and we dissolve it in water, the hydrochloric acid has the structure like this, and water, H2O, has a structure like this. What actually happens is the water acts as a base, and the base will grab a proton, so just the hydrogen, from the acid. The electrons in the HCl bond are actually left with the chlorine, which then becomes chloride. So what we're producing then, water grabs just a proton and becomes the hydronium ion, or H3O+. There's still one lone pair of electrons on the oxygen. And the chlorine becomes chloride. That pair of electrons got left behind with it, and so now it develops a negative charge. So our two species are ions that we form in solution when the molecular neutral acid HCl was initially dissolved. So we say this is an ionization reaction, and because our products become ions. There's a list of 7 strong acids that you're going to want to be able to recognize. Strong acids are acids that undergo 100% ionization, meaning they ionize completely when dissolved in water. The acids are perchloric acid, chloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. Any acid on this list, when it ionizes, so for example, if we look at hydrobromic acid, in water, will break up 100% into hydronium ions and bromide anions. This ionization occurs completely, which means hydrobromic acid is defined as a strong acid. All of the acids listed below will ionize 100%, which is what makes them strong. We're producing a lot of hydronium ion and a lot of bromide ion. Essentially, none of the molecular acid, such as HBr combined, is left together in solution. If an acid is not on our list of strong acids, then it must be a weak acid. The majority of acids are weak acids. Those are going to be substances that only partially ionize in water. So they don't ionize 100% like we saw with the strong acids. An example of a weak acid is something like acetic acid, which is found in vinegar. So if we compare what happens to acetic acid if we put it in water with what we just saw with hydrobromic acid, acetic acid in water will still form a little bit of hydronium ion when it ionizes, and a little bit of its anion, which in this case is the acetate anion, but it doesn't happen 100%. The ionization is incomplete. It might only be less than 5% for any given weak acid. And so what we use to represent the ionization of weak acids is something called double arrows instead of a single arrow. So we'll write an arrow going forward and an arrow going backwards. What this represents is chemical equilibrium. This means that the rate forward reaction is equal to the rate of the reverse reaction. So that means that the rate that the water is ripping a hydrogen ion off of our acetic acid to form hydronium ion and acetate is the same as the acetate ripping a proton off of the hydronium ion and going backwards to the molecular acetic acid and water. So we only have partial ionization with any weak acid. That means in solution, there's only a little bit of our ion species swimming around. There's not a whole lot of them, whereas before we had 100% ionization and there was a whole bunch of hydronium ion. Now there's only a small amount. This is what makes a weak acid weak in the first place. We learned that a base is something that produces hydroxide ions in water. A strong base is usually made up of a metal hydroxide that will completely dissociate, or in other words, completely ionize when in water. Metal hydroxides that are made up of group 1A metals and metal hydroxides that are made up of some of the group 2A metals are going to be strong bases that dissociate completely. So the group 1A hydroxides that are going to be strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. The group 2A metals that give us strong bases are calcium hydroxide, strontium hydroxide, and barium hydroxide. When any one of these bases is dissolved in water, it'll break up into its respective ions. So for example, if we put potassium hydroxide in water, that'll dissociate completely and give us aqueous potassium ions and aqueous hydroxide ions. The production of that hydroxide in water is what makes this a strong base. Same thing with the lithium hydroxide. If we dissolve some of that in water, we'll get aqueous lithium ions and we'll also get aqueous hydroxide ions. So this is an Arrhenius base. With weak bases, the hydroxide ion is not always easily seen in the chemical formula. Some substances will actually produce hydroxide ions because they chemically react with water, which changes them and gives us our hydroxide ions in solution. An example of this is something like ammonia, which is often in Windex. It will actually react with water, partially, not 100%, and it'll give us hydroxide ions in solution. So when we dissolve NH3 in water, we end up producing OH- and NH4+, which is the ammonium ion. The formula for this is we have NH3 plus H2O. And we're going to use double arrows, again, just like with weak acids, because now we have a weak base. The ammonia will grab a proton from the water because it's acting as a base. Therefore, the water is acting as an acid. And when it picks up a proton, it becomes NH4+, which is aqueous. And we're left with, from the water, OH-, which is also aqueous. Water is often described as being amphoteric, meaning it can act as an acid or a base depending upon who it's reacting with. We've seen water function as a base when it was with HCl, but here water's functioning as an acid because ammonia is a better base. If you take Chemistry 112, we will spend 3 chapters at least talking about acid-base chemistry more in depth. This is just an introduction into some of the things that can be acids or bases. Our goal is to use this information to write molecular, ionic, and net ionic equations for acid-base neutralization reactions at this point. An acid-base neutralization reaction is one where an acid and a base come together and neutralize each other to produce an ionic salt and water. Ionic salt and water will always be the 2 products from an acid-base neutralization. The identity of the salt will change depending upon what the acid and base are reacting. So in this example, we have hydrochloric acid plus sodium hydroxide, which produces sodium chloride and water. Hydrochloric acid has chloride as its anion, and sodium hydroxide has sodium as its cation. This is still a double replacement reaction where the sodium pairs up with the chloride to form sodium chloride. The other product comes from a proton combining with hydroxide anion. So we get H plus and OH minus, and what that really is water. So we can write H plus and OH minus as H2O. Just a reminder, an ionic salt is the name for any ionic compound, and ionic compounds are made up from metals and nonmetals together, or metals with polyatomic anions, because those are ionic in nature. Write the molecular, ionic, and net ionic equations for the following reaction. We have HCl, which is hydrochloric acid, plus KOH, which is potassium hydroxide. Hydrochloric acid is a strong acid. It's on our list of 7 strong acids. Potassium hydroxide is a strong base. We have a group 1A metal hydroxide. So when we do our double replacement reaction, we're going to have our cation potassium pair up with our anion chloride. We're going to get KCl as our formula, and that'll be aqueous or soluble from our solubility rules. And then we're going to form, that's our salt, we're going to also form water as our other product, and water is a pure liquid. So this would represent our molecular equation, where everything is represented as molecular species. Next, we're going to write our ionic equation, where we break up all of our soluble species, including our strong acids and strong bases, into their ions. So since hydrochloric acid is a strong acid, that means it's fully dissociated into H plus and Cl minus. Same thing with potassium hydroxide. That's a strong base, so it's fully dissociated into K plus and OH minus. Our products, KCl is soluble, so that'll be broken up into K plus and Cl minus. And we left our solid precipitates together. Whenever we form a pure liquid, just like a pure solid, those remain together in solution. So we don't want to break up our water. We're going to leave that as H2O liquid. This would represent our ionic equation. And then for our net ionic equation, remember we want to cancel out our spectator ions. So that's going to be what's the same on the left-hand side and the right-hand side. Notice we have potassium ions on the left and the right. and we have chloride anions on the left and the right. What this will reduce down to then is H plus OH minus, giving us H2O. So our net ionic reaction for an acid-base neutralization, when we have a strong acid and a strong base, is always going to be the same. It's always going to be hydrogen ions combining with hydroxide ions to form water. Now let's see how our equations change when we're dealing with a weak acid strong base neutralization. So in this reaction we have potassium hydroxide, which is a strong base, reacting with acetic acid, which is a weak acid. We would know it's a weak acid because it's not on our list of 7 strong acids. We're still going to write the products from our double replacement reaction. So we're going to form water, or H2O, and our salt that we're going to form is going to come from the potassium cation pairing up with our anion, which happens to be a polyatomic ion, which is acetate. KC2H3O2 would be our chemical formula for potassium acetate, and that would be soluble according to our solubility rules, so we would put aqueous after it. Now when we go to write our ionic equation from our molecular equation, we want to break up our soluble substances and our strong acids or strong bases. So potassium hydroxide will dissociate into K plus and OH minus in solution. But for our weak acid, acetic acid, we know that that is only partially ionized. It doesn't form many ions in solution at all. So whenever we have a weak acid or a weak base, we want to keep it together in our ionic equation because it really isn't dissociated into many ions. So we're going to write HC2, H3O2, AQ, keeping that together. And on our product side, we keep water together because it's a pure liquid. And we're going to break up our potassium acetate because it's soluble. So this would represent our ionic equation. Going to our net ionic equation, we're going to still cancel out our spectator ions. So potassium is on the left and the right hand side. And that's the only thing that's a spectator ion this time. We only have one ion that's going to cancel. So our net ionic equation is showing us what's really happening is the hydroxide ion is taking a proton from our acetic acid, our weak acid, and forming water, plus we're being left with acetate when a proton is removed from it. So that's our net ionic equation, which is showing the chemistry of what's really happening. So our proton is being removed from our hydroxide ion, ripping that off, giving us water and acetate for our net ionic equation. That's going to be the major difference you'll see when you have one thing that's weak, whether it's a weak acid or a weak base. You won't be left with just hydrogen ion, hydroxide ion forming water. You will still have some anion in solution. Let's try another example. Write the molecular, ionic, and net ionic equations for the following reaction. HClO3 is a strong acid called chloric acid, and BaOH2 is a strong base called barium hydroxide. Our products from double replacement are going to be water, H2O, plus the salt that's formed when barium cations combine with chlorate anions. Our formula here will be BaClO3 2 because barium is a +2 charge and chlorate is a -1 charge. If we use our solubility rules, we would see that the substance is going to be soluble, so aqueous. that would represent our molecular equation. We also want to check and make sure it's balanced. Notice that we have 2 on the outside of the hydroxide, which means there's 2 hydrogens and 2 oxygens that's representing. And we only have 1 chlorate unit on the left. We have 2 chlorate units on the right. So we're going to put a 2 out in front of our HClO3. And now we need to check. We have 4 hydrogens on the left, and we only have 2 hydrogens on the right. So we're going to put a 2 out in front of our H2O. That gives us 2 oxygens and 4 hydrogens, and same thing on the left, 2 oxygens and 4 hydrogens. Now we can write our net ionic equation, or our ionic equation first. So when our strong acid dissociates or ionizes, it'll ionize 100%. So we're going to get 2H plus, because we have a coefficient of 2 out in front, plus 2ClO3 minus. Our barium hydroxide is a strong base. That'll fully dissociate in solution. Ba2 plus 2OH minus. That comes from the 2 right here. The subscript after the hydroxide. H2O. We don't want to break that up. It'll be just 2H2O, which is a pure liquid. And our other product, barium chlorate, is going to be soluble. So we'll get Ba2 plus and 2ClO3 minus. Our spectator ions in this case are going to be the barium ions and the chlorate anions. Our net ionic equation now is going to be 2H plus 2OH minus, giving us 2H2O. And if you want to reduce that down even further, to simplify, you could write H plus OH minus, giving us H2O. So either one of these would represent our net ionic equation. And that's what we would have expected because we had a strong acid, strong base neutralization. In this reaction, we have sulfuric acid, which is a strong acid, reacting with rubidium hydroxide, which is a strong base. So our products are going to be H2O plus our salt we're going to form will be rubidium sulfate. Rubidium is a +1 cation, and sulfate is a -2 polyatomic ion. So our formula will be Rb2SO4. This should be soluble, so aqueous. And then we want to check and make sure everything is balanced first. So notice we have 2 rubidiums on the right, so we're going to put a 2 out in front on the left. And we have a diprotic acid, which means that sulfuric acid has 2 protons for every 1 anion. So we have a total of 4 hydrogens on the left-hand side, and we need to have 4 on the right, so we put a 2 out in front. And everything else should be balanced now. We're going to break up our soluble substances and our strong acids and bases for our ionic equation. When sulfuric acid dissociates or ionizes, we get 2 hydrogen ions because there is that subscript of 2 right there. We're going to get 1 sulfate anion. When we break up our strong base, we're going to get 2 rubidium ions, each a +1 charge, plus we're going to get 2 hydroxide anions. Onto our product side, we form 2H2O, and then from our rubidium sulfate, we'll get 2 rubidium ions and 1 sulfate anion. Our spectator ions, in this case, are going to be our rubidium ions. Those will cancel. And our sulfate anions will cancel. What we're left with then is just what we saw in our last example, 2H plus 2H minus, giving us 2H2O liquid. So we had a strong acid, strong base, and our net ionic reaction was hydrogen ions combining with hydroxide ions to form water.